record this. So we're recording as we speak. Okay. And so the idea was, as you might recall, many of you who were part of this at the beginning, we didn't want to have researchers falling all over themselves trying to get the same funding for this work. We wanted to take a collaborative approach. So that's what we did. So we now have a nice collaboration among all these folks here. And the idea was that we would develop in the Northwest in partnership with other regions to the extent possible, blue carbon as a way to address and help mitigate climate change issues out here. Speaking of the working group, I wanted to shamelessly plug the working group workshop that we're going to have on St. Patrick's Day, so March 17th, half-day meeting. So please feel free to join us if you're not already planning to. We will be talking about larger working group issues, a bunch of the issues that sort of next step issues for the working group. So another shameless plug is that we have a website, in case you're not already aware. It's got a bunch of background info and project info and documents. It's not huge because we're just getting started, and I would like to sort of shore up the data part of that at some point soon. It includes a link to our Twitter page. I'm not a Twitter person, so I think people who know Twitter should use that. I should know more about that, but I don't. Okay, so where have we been? We have gone to the National Estuarine Research Reserve System Science Collaborative a few times now, and they've been very supportive of the working group's work. So starting in 2016, we got started with a high priority data gap filling of carbon stocks, and we wanted to establish a blue carbon database for the region. So that's what the focus of what we're now calling the phase 1 project was. And we've been able to end up with a publication that focused on carbon stocks in least disturbed sites in the region. And then in development, Chris has a couple of papers focusing on the ecosystem driver relationships with those carbon stocks, and what we're calling a data synthesis for the database. There are some Pew people on this call, and I would like to just point out that they're helping us make those 2 papers happen more efficiently than we once hoped we would be able to do. Right in the middle of that project, some of us, here's where Steve Crooks jumped in and said, why don't we take some of the data that are already existing and the new data being collected and apply them to testing out what the possibilities for doing carbon projects would be in what turned out to be 3 systems. So we ended up with a scoping assessment for those 3 systems. We learned a great deal about the possibilities and the limitations for carbon finance projects in the Northwest, and very importantly, refined, reinforced, and learned new data gaps that we needed to address. So building on those 2 projects, we again went back to the Near Science Collaborative for this phase 2 project. understanding that we still have data gaps in greenhouse gas flux and carbon sequestration, and importantly, in a wider variety of land uses. So we have developed that project as, again, building on to the previous projects. Meanwhile, there are a couple of projects that are critically related to the phase 2 project. One has already been started and finished, and this is where Scott Bridgham and his grad student, Matthew Schultz, and Laura Brophy teamed up, and others collecting blue carbon data, and importantly, greenhouse gas emissions data at a site in at sites in the Tillamook system. And then more recently, Chris Janicek leading the development of this ecological effects of sea level rise project, also includes an important element of greenhouse gas emissions, and that project is underway. So combining the effort that we have in the phase 2 project, we realize that we have a really nice situation here where we can lean on two other projects as companion projects to develop a really effective whole. And I'll explain a little bit more about the geographic scope in a second. A little water break. So we have a great project team here, and hopefully many of you can see your names on here. We've expanded the team even from the proposal. And so we're essentially looking at, with the phase 2 project, 5 objectives, again, focusing on filling gas emissions and carbon sequestration data gaps for major tidal wetland classes and land uses, and just to reiterate, least disturbed ag lands and restored lands. We want to examine how net ecosystem carbon balance, which is carbon sequestration minus greenhouse gas emissions, compares among those wetland types and land uses. And then, of course, we want to collect the data, quantify the ecosystem drivers for those sites, and establish relationships between those and the data collected. And then we definitely want to continue to expand the blue carbon database, and there's some important connections to be made there. And last but not least, we really want to continue to engage end users to make sure that this work meets your needs. So geographically speaking, again, the phase 2 project, and you'll get this reinforced in the following presentations, really focuses on 2 sites up in Washington, Skagit and Johns River systems. And the companion projects that we're working with, the Eastler project, Chris's project, are centered on Lower Columbia Estuary sites and sites in the Coos Estuary. And then Scott's project is located in the Tillamook Estuary. So between a really great project team, meaningful objectives, and a reasonably wide geographic range here, I think we've got a pretty good project here to really fill some regional data gaps. Blue carbon data gaps. So timeline-wise, we are at the beginning here. Today we are looking at the we're doing the first, what we're calling steering committee meeting. And then we're just getting started with the field work here. Data analysis throughout, database expansion throughout, and hopefully end up getting some manuscripts done. So the why of it all, where are we going with this? We have a great interest in continuing to expand the database. And as many of you know, we're partnering up with Smithsonian Environmental Research Center's Coastal Carbon Atlas on that, and also the NEAR's CDMO, Centralized Data Management Office, so the data live in multiple places. And then continuing to do publications in the form of the data synthesis and other publications. And then now that we are getting to the point where we have some handle on some of these data gaps, we can start to think next phase for the working group. And that means contributions to Northwest natural climate solutions initiatives. And that includes the one that Steve Crooks mentioned, inventory for natural and working lands effort in Oregon. And recently an effort that Scott brought the Blue Carbon folks into, which is establishing for the Northwest a natural climate solutions network. And so that's a proposal that we'll hear about. That is about it. That should be a reasonable context for what we have going on here. And I'll just end the slide with a nice serene day on South Slough to help me calm down. Any questions? Okay.
Craig, it says that participant screen sharing is disabled.
I have to enable that.
Thank you.
I don't know why that's the default. All participants. Okay, should be good.
While you're enabling that, let's see.
All right, so no questions about the context. We are going to push ahead here with Haida and Scott's presentations about the gas emissions research part of the project.
Okay, can you hear me and see the slide? All right, good morning, everyone. I was just hearing all the introductions. I was remembering that the last time I saw some of you was when we could still go out and have a beer after the last end users workshop from phase 1 and up at the Tulalip tribe. So things have changed a lot since then. It's really great to see you all and hear you all. And I'm really appreciative of your continuing interest in this work in the Northwest. And thanks, Craig, for a great introduction and all your coordination work. So today, Scott Bridgham from the University of Oregon and I are going to present one of the components that you saw built into the phase 2 objectives, the greenhouse gas emissions component. And others involved with leading this component and the field data collection are Amy Bordy from the Pacific Northwest National Labs Marine and Coastal Research Lab, Jude Apple and Roger Fuller from the Padilla Bay National Estuarine Research Reserve, and 2 postdocs, Maggie McKeon and Matt Norwood. So just to set the stage for this talk and the following talks, I'm going to go ahead and go over the research questions in detail, and you will see these again in the subsequent talks. As you can see, I'm highlighting our component, the greenhouse gas emissions, in yellow. And in this particular research question, you'll also see sequestration rates, which as Katrina mentioned, she and John Ribzik are working on. So the first question is, how do greenhouse gas emissions, sequestration rates, and NEE vary between essentially land cover types? So least disturbed tidal wetland types, which are going to be emergent marshes and forested tidal wetlands, and between these least disturbed types and disturbed former tidal wetlands and restored sites. The second question concerns environmental factors, controlling factors, ecosystem drivers, and you'll see a presentation from Chris Janicek later today on this research question. So the question is, how do environmental drivers such as soil temperature and salinity, groundwater level, photosynthetically active radiation, and wetland elevation influence the greenhouse gas fluxes, sequestration rates, and net ecosystem exchange? And the relationships, just to set this up for Chris, the relationships between these environmental factors that we establish, both here and in the prior phase 1 study, are intended to be able to allow extrapolation to other sites, and ultimately modeling and predictive modeling and utility for the finance team that Craig mentioned. The final question is, how does net ecosystem carbon balance, so as Craig mentioned, sequestration minus the greenhouse gas emissions, differ among the wetland types in the Northwest, and which wetland types are best suited for carbon sequestration focused restoration? Okay, so turning to the gas emissions component of phase 2, this is very complementary with the concurrent NOAA-funded Effects of Sea Level Rise program project. And Craig has introduced the map, which I'll be showing again a couple of times, because really we're going to be collecting data concurrently using the same methods in terms of greenhouse gas emissions. And I want to assure everyone that our technicians and postdocs will all be meeting together in about a month to calibrate the methods before any data are collected on both of these projects in the gas emissions component. So the overall goal that is a common goal between these two projects, the NOAA ISLA project has a very unique aim from our phase 2 project. And several of us on this call are co-PIs with Chris Janicek on the NOAA ISLA project. But its unique aim is to assess the effects of potential coastal wetland restoration scenarios on the protection of coastal infrastructure under sea level rise scenarios. So the ISLA project, although it is collecting greenhouse gas emissions data as a co-benefit, its focus is really on infrastructure resilience. It's very modeling intensive. It will involve both hydrodynamic modeling using FVCOM, the finite volume coastal ocean model, and the warmer model that many of you are familiar with. But fortunately, we will be able to obtain greenhouse gas emissions data from both projects. So the common goal of the two projects is to quantify the variability of methane emissions in Pacific Northwest coastal wetland complexes. And this, of course, was identified by the finance team and by the science team as well over the last couple of years as a major data gap, a major uncertainty affecting the ability to predict the net ecosystem carbon balance, particularly along these salinity gradients, where the tidal freshwater ecosystems that we have, including the tidal forests, may be methane sources, and that remains to be determined. So that's the rationale that I've just gone over, is that the high priority of the lack of methane data in restored tidal wetlands and in the pastures that are available for restoration, because the initial analysis by Scott Settlemyer and Steve Crooks and others showed that the pastures themselves in the Northwest do store quite a bit of carbon. So that net difference between our baseline, our pre-restoration baseline, and post-restoration is something that needs to be, we need to drill in and get more accurate information that allows predictions. So our objectives, again, the common objectives between these two projects are overall to collect new emissions data from 4 wetland complexes over 1 full year, starting in March. And then to analyze the data, of course, and the Eastler project will use it to conduct warmer modeling and to make the data available to end users and the database. And the database is another talk that you're going to see later on today from Chris. So back to the map, and as Craig mentioned, these sites in orange are the sites that we're actively collecting data on for phase 2. Scott Bridgham and a graduate student, have previously collected data on the Tillamook estuary, which he'll be showing today later in this talk. Some examples to get a sense of what the results are that we're ultimately going to see from phase 2. And then the companion project, the NOAA Eastler project, is collecting data here on the Lower Columbia River estuary and the Coast estuary. So the common research question 1, or the research question 1 for phase for gas emissions, just for the gas emissions component here, is how do methane emissions vary along the estuarine salinity gradient? And our sites do represent 4 salinity classes from freshwater to oligohaline, mesohaline, and polyhaline. So for those of you who aren't from the region, I just wanted to show sort of a typical wetland complex in the Northwest, where at the upper reaches, we have Sitka spruce swamp. They're known as tidelands spruce. They have some resistance to salt, some tolerance to salt, spray, and groundwater. And it tends to trend down the elevation gradient to a shrub scrub type cover type, with willows and red osier dogwood and so forth, which is just a fringe in this particular picture along the edge of the spruce swamp. And then high marsh, which you can see in green here, and low marsh as you go down the gradient, down the channel to the mud flats. And this picture also shows an example pasture, another one of our land cover types. So the second primary research question is how does land use or land cover type affect greenhouse gas emissions? And again, this emerged as an uncertainty from phase 1 that was crucial for finance analyses aimed toward voluntary carbon offsets for restoration. So our sites represent 6 land cover classes. In the least disturbed category are tidal marsh and swamp. And then we have restored tidal marsh and swamp. And I'd like to note that this is a bit of a misnomer to call the swamp restored, because it will take hundreds of years for the overstory to reach even a mature, much less old growth status in these tidal swamps. And I could go on and on about that, but this isn't the place. So, but we'll look at places that are early stage, very early stage swamp restoration sites. And then both wet and dry pastures, which again emerged as a data gap in phase 1. Just a few closer up images here. This is an emergent marsh on the Columbia River at the left, with Wapato, a typical tidal freshwater plant. These plants, we will be, as Chris will talk about, we will be collecting vegetation data on these new sites during the course of the next year, well, longer than a year, I think next summer. But these are just some example key dominant species from other similar sites that we've sampled previously. So our primary least disturbed types in phase 2 are the emergent marsh and the Sitka spruce forested wetland that you see here. So we are, as I mentioned, coordinating the methods for the NOAA NERS and the Eastler data collection, the greenhouse gas emissions data collection. and very closely. And so for phase 2, the minimum number of sites per wetland complex is 7. I think we're actually up to quite a bit more now. And these will be sampled every 6 weeks for a year, starting in late March of this year. And each site, so again, each wetland complex is made up of a set of sites representing these different land cover classes. And the number of chambers per site will be 6. And then both phase 2 and Eastler will use light and dark greenhouse gas emission sampling. And the equipment will be the LICOR for phase 2 and the GasMet for Eastler, and boardwalks are being or have been constructed at all sites to avoid confounding factors. So with that, I'm going to turn it over to Professor Bridgham to talk about his previous Tillamook research. Thank you.
Actually, Haida, I changed a slide. So if you could unshare, I'm going to share from me.
Yes, I think I can do that. Give me a moment.
Stop sharing. Okay, and then I will share my screen. Okay. Thanks, everybody, and it's great to see virtually everyone here. And so, as Haida mentioned, a graduate student of mine, Matthew Schultz, did his master's thesis looking at greenhouse gas emissions and large restoration in Tillamook in collaboration with several other people who are here, particularly Laura Brophy and Chris Janasek. And so I'm going to share some of those results with you here. And so this is a very large restoration, about over 440 acres. And so we had 12 greenhouse gas sampling sites in this large restoration area. And we did it pretty soon after restoration, beginning a little less than 1 year after restoration. We also had 3 reference sites, which were all high marshes. And we also sampled 3 adjacent agricultural fields, all of which were former tidal sites. And sort of the assumption is that maybe they would have reflected their restoration site before restoration. We used the same methods as is going to be used in the ongoing projects, with sampling 8 sampling points over a year, 6 chambers per site, and the same ecosystem driver variables that Chris Janasek is going to be discussing a little bit later, and I'll show you some data with those versus methane in just a second. And you can see on the right here with the photos, this is a pretty simple way to do things. We have a boardwalk, so walking on the surface doesn't express gas into the chambers. And then we have a chamber bottom here, which we leave in over the entire period. And then we're sampling, this is a dark chamber, we put that on the base, and then it's hooked up to a GasMet where we measure the emissions of gases for a relatively short period of time. It's about 10 minutes. This is a spaghetti diagram of data, but it gives you some sense of what we saw. And the title actually has the main message, is we saw very complex nonlinear environmental controls over methane emissions. And that's the main point to get out of this, but I will describe it a little bit. So in red, we had the disturbed sites, green, the reference sites, and in blue, the restored sites. And on the y-axis in each case, we have the micromoles of methane emissions per meter squared per minute versus the various environmental drivers that we measured. And if those of you who haven't taken statistics in a little while, the R squared can be interpreted as the amount of variation that is explained by the simple linear regression. And so in this case, methane versus water table, the R squared is 0.013, which means we can explain about 1% of the variation in methane emissions by water table. Not very much, but it's also highly statistically significant. And this is just a good case to look at, as you could see that clearly water table matters. If it's very dry or very wet, we don't get high methane emissions, but someplace in the middle we do. And you could note that the restored sites, because of their subsidence and probably because lack of adequate drainage, were quite a bit wetter than most of the other sites. And because of that, they have higher methane. And I'm not going to go over this too much, but you could see that same sort of thing with air temperature and soil temperature, that there is sort of a relationship. You don't get emissions when it's very cold, but if it's warm, it doesn't mean you will have high emissions. Salinity is particularly important because of the salinity gradients in estuaries. And so on the bottom left here, you could see that if it's pretty fresh, basically oligohaline or fresh, is that you could see that we can get high emissions, but if it's more saline than that, we generally don't get high emissions. And other experiments in other estuaries have found similar things, although it might go a little more into the saline, yet emissions being a little more saline. And you can see that there's kind of some vague relationship maybe with pH, where you don't get high emissions at low pH, and percent carbon, there didn't appear to be much of an effect, just looking at it that way. So what do you do with something like this? And the answer is you use fancy statistics. So we use something called classification and regression trees, which are a really good way to look at interactions and nonlinear effects on things. And so on the bottom here are what's called lees. And each of these, we have 5 different groups. And so you could see, and they go from left to right to higher methane emissions. And so you could see the one on the right has the highest methane emissions. And the second one to the right also has relatively high emissions. And the ones on the left have progressively lower emissions, but all are low. And so the way this works is it sort of bifurcates the data. And so if you have a water table that's further than 1.5 centimeters from the surface, so quite close, you get really low methane emissions. If it's higher than that, and if the air temperature is greater than 24 degrees Celsius, you get very high emissions. If the temperature is a little bit lower, but the pH is high, greater, it's basically circumneutral, 7, and the salinity is quite low, so it's quite fresh, you also get high emissions. But in all other cases, you get low emissions. And this explained 28% of the variance in the data. Not great, but certainly a lot better than the other, sort of just looking at the linear effects. One of the main things we wanted to look at, obviously, in this is how does the different land uses affect methane fluxes. We also looked at nitrous oxide, another very potent greenhouse gas, over here on the right. And on the top are the instantaneous emissions that we measured. And on the bottom, we annualized these just by interpolating between the dates that we did it. And so for methane, which is this left-hand column, if the letters are different, that means they're statistically different to different land uses. And so you could see for both instantaneous and annual that the restored sites have about, on average, 10 times higher methane emissions than both the reference sites and the restored and the disturbed sites. Make sure I said that right. The restored sites had about 10 times higher methane emissions than the disturbed and reference sites, both instantaneously and annually. And again, I think that's because they tended to be much wetter, and hopefully as they gained sediments over time, that they will have lower methane emissions as they move up in the profile, and also maybe as we get better drainage in the site through tidal channel development. Nitrous oxide emissions, there are some significant differences. The main thing is you can see this is times 10 to the 3. These are very low emissions, and basically it was not significant in terms of greenhouse gas forcing. And that include the farm fields, which are the disturbed sites here. So that suggests that the nitrogen fertilization is not causing lots of nitrous oxide emissions. So basically that's good. Another point to make is just variation. Again, this was a very large restoration site. And so here we're looking at the methane emissions on the left panel versus the individual sites. And each of the points is a sampling, instantaneous sampling point. And so you can see there is massive variation here. And on the right, it's the same data. We just cut it off at 8 so that you could get a better sense of taking the really high outliers out of this. And again, you can see the same thing. And the sites in blue are the restored sites. And you can just see how varied the methane emissions were. Again, predicted by the things that were in the classification and regression tree, particularly important being water table and salinity. And so in this really large restoration site, different places had very different greenhouse gas dynamics. And that's certainly something that will be important, thinking about how to manage these, and if one are going to use it, for example, for carbon markets. It would make it very difficult. So what are the project outputs that we're going to have? This is for the overall, for both the former project and the ongoing ones. So as Haida mentioned, with soil carbon sequestration data, we can calculate the climate warming cooling effects of land uses across these salinity gradients. We'll obviously have publications and NOAA reports with this, which will be publicly available. The data itself will be publicly available, and we're working with a group of scientists who are now putting together all of the greenhouse gas data for coastal wetlands in the continental United States. And that is being analyzed and will probably be published maybe sometime later this year. And obviously, we want to make sure that we work with stakeholder groups with like this through the Pacific Northwest Blue Carbon Working Group. And then lastly, just some discussion questions, depending on how we have a few minutes, are there questions about methods, priorities related to greenhouse gas emissions, questions or comments about our approach and field methods? So how can we make sure that what we're doing fits the needs of the stakeholders with this project? And so with that, I'm going to stop sharing and open it up for comments.
Thanks, Scott. Anyone have any comments about what Haida and Scott have presented? Okay.
Well, there have been some comments and questions in the chat. I don't know if you want to address those.
Oh, right. Anybody who's been chatting, would they like to bring up their comments to the group? I don't want to put anybody on the spot.
Hey, this is John Ripsick. Scott, just I was wondering, nice, both of you, nice presentation, by the way. Could you speculate as to why methane emissions were so high in restored sites compared to the other sites? I would have hypothesized the opposite.
Yeah, so I think that it basically had to do with the hydrology of the sites mostly. And you could see also in that classification and regression tree, that was the most important variable. And the restored sites were much wetter than the other sites. We compared them to high marsh reference sites, which they probably were close to or maybe even higher historically. And also to agricultural sites, which were diked and drained, although they did have standing water in the summer. I mean, in the winter, in the rainy season. And I think it's because they subsided, so they're lower in the profile historically when they were drained. And then when the site was done, the drainage channels probably could have been done better to drain the water off the site. And Laura Brophy, you know the hydrology very well of this large restoration site, and maybe you could speak a little more to that.
Yeah, thank you. It is really common at these restoration sites to have standing water after restoration. So a big tide comes in, the channel network that's been dug is nothing like the density present in a least disturbed system. You might have 1/10 the channel density. So you end up with standing water on the surface throughout the tide cycle. And that's particularly characteristic of the 2 or 3 locations on that 400-acre site that were responsible for those big methane emissions. So I remember always being, mid-calf deep in water at those sites, regardless of where you were in the tide cycle. So I think that's what's going on. And there may be other factors we didn't measure, which contribute to the low explanatory power of the variables that we measured, possibly related to vegetation decomposition or something like that. And Scott could probably speculate a lot more intelligently about that than me. But those sites that leaked a lot of methane were distinctively wet and impounded constantly.
They're constantly reduced and anaerobic then is what you're leading to then, right?
Yeah, and there's management implications for this. If you can excavate more channels when you do a restoration, it's going to have a huge impact on this kind of thing.
Laura, what kind of rate of channel development have you seen on the outer coast or places like Tillamook Bay? I mean, because we use the same type of methods, kind of passive restoration methods on the Columbia, where they kind of, I forget what the word is, but they do kind of they initiate a channel and they expect that the tidal action is going to build out the channel network over time. I'm just wondering if you've monitored the rates of that.
We've kind of tried. It's really challenging to define what is a channel in a system that's still in its first decade of restoration. You have a lot of poorly defined drainages of all kinds and shapes and sizes and directions, and the network is not well defined. So it's hard to evaluate that, but I would say it's going to take decades, just noticing how channels often downcut with an erosional formation process or build up slowly with an accretionary process, and those are decades-long processes.
Hey, you guys, just to keep us on time, I'm going to jump in here and get us to our break. If you guys want to keep discussing during the break, that is fine with me.
Could I have one last comment before
Yes.
that? Is to add on to what Laura said. These sites also accumulate sediments quite rapidly, and so they will move higher in the soil profile just through that, and likely become more like the high marsh sites just through moving higher elevation through time. But again, likely decades.
Okay, I'm going to start a countdown timer. I don't know if this is obnoxious. Let me know if it is.
The scenery is nice, but the numbers are obnoxious. They're kind of in the way.
They are, aren't they? This was the nicest one I could find. All right, talk to you guys in about 5 minutes. I'm gonna sign off for a sec.
What?
I'm feeling a lot of pressure.
Yep.
And then there's a restroom at the end of the hall.
Already used it.
Awesome.
Are we on a break?
Yeah, just a break for a couple minutes.
Cool.
How was the drive?
Lovely.
I see.
No, there's some beautiful sun breaks. It was really
Hey.
nice.
Hey, Trevor.
Hi, can you hear me?
Yeah, nice to meet you. This is
Nice to
Craig
meet you
down the
too.
hall.
Oh, hi. Here, I'll put my video on so you can see, maybe. Oh, Duke. Hello.
Hi. You're just in time for the break, so I'm
Yes.
gonna
Perfect
maybe
timing.
swing down and say hi.
Okay, great. How many folks we got?
I got hailed on a little bit this morning.
You did?
Well, the car did.
Were you in Portland this morning?
No, I drove down last night.
Oh, nice.
Hey, nice to meet you.
Hi, you too. How's it going?
We would shake hands in a manly way if we could.
Be one of
I
those.
can't shake hands for a year.
I know. Well, with these COVID bears, are you on mute?
No.
Keep in mind that when you leave, I don't remember, they like you to take the white, everything down.
Well, at least with COVID, the queues during the breaks are quite short.
Craig, I didn't realize there was a timer like that. I've got to find it because I teach my class and give them a 5-minute break in the 2-hour class too, and I didn't.
If you like that one, I
realize there
can
was
share you. I can show you the link, but share the link with you. But oh, hang on.
Oh, it's not part. It's not part of Zoom.
No, it's
Oh, okay,
just
all right.
a here.
Share the
I-
screen with the timer. Yeah, I got you. Yeah.
I have to throw Chris a key. Okay, welcome back, everybody. Without further ado, let's jump into Katrina and John's part of this presentation. Does anyone have any issues or questions before we get started? Everybody's happy? Everyone's back from the break? I can't tell. It's
Hey, Greg.
yes.
This is Jude. Hello, everyone. Will we have a chance to circle back for a little informal Q&A at some point? There's some stuff that came up during Scott's presentation, and there's some sort of head scratching I think a lot of us are doing about just the messaging surrounding this data that I'd love to talk through a little.
Okay, so let's find a time for that as we go through here, and we might be collecting these kinds of things as we go through presentations. But I don't want to impinge on Katrina's time too much here. Okay, Katrina, take it away.
Okay, one moment. All right, all looks good.
Yes.
Yep.
Great.
Looks good, Katrina.
Okay, so this next talk is about the carbon sequestration component of this project, and that's led by Dr. John Ribzik and myself, Katrina Poppy. And I'll do the honors of giving this talk, but John is also here to help answer questions. And I'm also hoping he'll interrupt at any point to tell jokes.
Hey.
So we'll put this in the context of those three main research questions again. So hopefully by the end of this meeting, you'll be quite familiar with these. So first question, from the standpoint of our carbon sequestration rates, is how do carbon sequestration rates vary between wetland types, like marshes and tidal forests, and between land use types, like restored or converted ag lands, etc. Second, what are the main environmental drivers of, again, in this case, carbon sequestration rates? And third, so we want to estimate the net ecosystem carbon balance for each wetland type and each land use type. So in other words, essentially find out if they're a net carbon source or a sink. And carbon sequestration rates are an important part of that equation. So sequestration rates is carbon coming into the system. GHG emissions are what's coming out. And the difference between those two is what's really most relevant for carbon market projects. So as you can see, the carbon sequestration rates are an important part of all three of those questions. And a little background to help emphasize why we think the carbon sequestration rates are so scientifically important. Our past work, largely in the Puget Sound, has shown us that our marshes tend to have relatively low soil carbon densities relative to what others are seeing in other parts of the US and worldwide. But on the other hand, we're also seeing relatively high soil accretion rates, and in most cases higher than the recent rate of sea level rise. So carbon sequestration rates are basically the product of soil carbon density and accretion rates. And it's appearing that the sequestration rates are more sensitive to accretion than carbon density. And I'm saying this because I think it's good news. If we want high sequestration rates, it means that even if we have kind of a low carbon content, as long as we have a decent accretion rate, we can still get a decent sequestration rate. And from our past work, we've also found some of these data gaps, which probably won't surprise any of you. There can be a lot of variation in accretion rates, even within estuaries. So we need more work, and this project is going to help a lot with this. to really understand what's driving that variation in accretion rates, and also just help us get a better idea of what kind of replication we need within a site to really characterize it well. And then we also, we have some data from natural or least disturbed wetlands, but the recently restored or converted ag sites are particularly data poor. So we're particularly excited about this project because it will really help with some of these lingering questions. So study sites, we focus on 2 estuaries for this project, which I've circled, Skagit Estuary and the Johns River Estuary. And then, which you've already seen this, but again, there's those 3 other estuaries that are part of related companion projects. But for this talk, we're just focusing on this particular project in these 2 estuaries. Both of those estuaries will have 7 or 8 sites per estuary that are an attempt to represent a variety of wetland types, marsh and swamp, a variety of land use types, least disturbed, restored, and ag land, and different salinity classes. So now I'll get into our proposed methodology for the accretion rates. And the accretion rates are really very important. They're kind of at the heart of this part of the project. And, and so I'll describe in the next few slides why we decided on a combination of 3 different methods. And I'll begin with an overview of each of the 3 methods. And hopefully it'll be clarifying more than confusing. So the first is sediment cores, of course, and we use sediment cores and date them with radioisotopes like lead-210 and cesium-137. So when your end goal is long-term carbon sequestration rates, this is the generally accepted standard method to determine long-term accretion rates because of its long time frame. So what's really great about cores is you can take the core anytime and you instantly get about 100 years worth of information. So you can get a really nice long-term average accretion rate that does a nice job of smoothing out short-term year-to-year variation. And this is typically what we do for all our blue carbon work, but one major disadvantage of this method is that the radiometric dating is very sensitive to any sediment mixing. And so this is especially pertinent to this project where we have disturbed ag sites, especially if they're tilled, that's very mixed, or even recently restored sites. Basically any site where the sediment is mixed or messy, this can be difficult. So enter the second option, which is surface elevation tables, or also known as sets. So the set is a bunch of hardware that you install as a permanent benchmark. And it has rods that go several meters deep. And then you return regularly to monitor the surface elevation relative to your benchmark. Some pros, the set is very stable and reliable, and it's very deep. So your measurement will incorporate accretion, both short-term accretion near the surface, as well as shallow subsidence deeper down. Another major advantage is that it's not sensitive to sediment mixing. So we can use the set in disturbed, oops, I got excited there. We can use the set in disturbed and restored sites. One downside though is that you have to worry about year-to-year variation. So as you might imagine, the longer you measure a set, and you can theoretically measure them indefinitely, the longer you measure it, the better your data will be. We've had some sets out in Padilla Bay for nearly 20 years now. And so those trends are looking pretty solid at this point. But when you just have a year or two of data, the data are going to look a little bit noisier. Lastly, the feldspar. And feldspar is a clay layer that you sprinkle on the surface of the mud, and you return to it over the next few years to measure visually the depth of sediment that's accumulated on top of that layer. So this is just measuring what's going on at the very surface. So it's just very new sediment inputs. So unlike the cores and the sets, the feldspar does not incorporate deeper processes. And the deeper is where a lot of the decomposition and compaction is happening. So because feldspar measures much shorter term accretion, we don't use it to calculate long-term carbon sequestration rates. But what feldspar can do nicely is provide a relatively cheap and easy way to compare one site to another, short-term accretion. And they can also help us to tease apart what's accreting at the surface versus what's subsiding below the surface. If you have both feldspar and sets at the same site, you can compare the data that way. One disadvantage, though, is that similar to the sets, the feldspar is sensitive to short-term variation. And not only that, the rate you report from feldspar is also dependent on your monitoring time frame, how long you measure it. And so that's what this figure on this slide illustrates pretty well. And I'm going to try to explain it briefly without getting too off track. So say what you measure in year 1, that's that first block, that first sediment cohort. What you measure in year 1 is not going to be doubled in year 2, because what you measure in year 2 is the year 2 sediment cohort now on top, plus the year 1 sediment cohort that at that point has now been decomposed and compacted quite a bit. And so at the end of it, say you go back out to measure your sediment accretion on top of the feldspar layer after 5 years, and then you divide that cumulative amount of accretion, you divide that after 5 years, divide it by 5 to get an annual accretion rate. And that annual accretion rate is going to be much smaller than the annual accretion rate you would get from year 1, say. So I hope that helped you understand a little bit why both the time frame of your method is important, because a lot of these sediment processes are happening all the time, and as well as the depth that your method incorporates. Both those two things are important, and they differ from one method to the next. John, did you want to say something?
Yeah, I want to also jump in here. That graph, you could move that x-axis, for 100 years, and you get the same kind of illustration for why we would use a set, or lead-210, because those processes don't magically stop after 5 years. They are going on and on and on. So if you want to get an estimate of long-term accretion, then at equilibrium, then the lead-210 and the cesium would be the gold standard.
Yes. So as you can imagine, if you just use feldspar, and after 1 year, you're going to get a relatively high 1-year accretion rate compared to what you would get from all those other methods that incorporate those processes over a longer period of time. So we just need to keep all this in mind, and ideally use the same method or the same time frame when you're comparing one site to another with feldspar, or with any method really. So I hope that all gave you a sense of how each method has its pros and cons, but each also has its purpose. But for this project in particular, here's what we decided to do. Basically throwing everything in there. So we're going to try taking 2 cores per site and get accretion rates that way. But we're also adding sets to the disturbed and restored sites as a backup in case the lead-210 dating doesn't work out at those sites. and add feldspar to every site as an added bit of consistency. And one side benefit to using all three methods is that we'll be able to do a little methods comparison and see how they compare at any given site, because not that many other studies have done that. And I think that would be valuable. So here's what we'll do with the sediment cores. We'll take at least 50 centimeters depth core, slice it into 2 centimeter sections, and analyze each section for bulk density, percent organic matter, percent organic carbon, and use gamma spectrometry to look at lead-210 and cesium-137 trends down core. And from all that, we can report an overall carbon density and accretion rates, and of course, carbon sequestration rates for each core. And I added this figure here of an example core profile of organic matter, just to demonstrate how this is pretty typical in that there's a lot of organic matter at the top. That's where a lot of it is coming in, and then a lot of decomposition happens near the surface. And then typically we tend to see like this, the organic matter as well as the carbon stabilizing at some point deeper down. And so it doesn't decompose to 0. In this case, it's stabilized around 3 or 4%. And so that's really what we're referring to. That's really the carbon that we're looking at when we refer to long-term carbon sequestration. That's what's getting sequestered. For sets and feldspar, I'll just briefly say that both sets and feldspar get installed in year 1 and measured at least once a year after that. They both involve a fair bit of replication per site, which helps to smooth out any small scale topographical variation. And we also plan to take some supplemental field data associated with each core, because we plan to eventually submit our core data to some databases for archiving, including the Pacific Northwest Blue Carbon Database, which Chris will tell you about later, as well as the Smithsonian's Coastal Carbon Research Coordination Network database, which is fabulous and highly recommended. Timeline. I already talked about this a bit, but so the cores will do all the core collecting in year 1, and then all the analyses in years 2 and 3. The lead-210 dating takes forever, so that is going to probably take the entire 3 years. Sets and feldspar will install in year 1, and then annual measurements at least after that. In terms of the data that we produce, this is just for this component of the project specifically. We'll produce core profiles or depth series data sets on bulk density, percent organic matter, percent carbon, carbon density, and lead-210 and cesium-137. We'll also report rates of accretion, of course, both long-term and short-term rates, rates of elevation change from the sets, and of course, calculated rates of carbon sequestration. And all of these outputs will be organized by wetland type and by land use type. So this should allow you to easily compare sequestration rates, say in a pasture versus a recently restored marsh, if that's what you're interested in. So here's our last discussion slide, and we've seeded it with a couple questions, and then we'll open it up to whatever else. First, so I just mentioned in the previous slide how the data will be organized, but since the whole part of this project is to make it useful to you, we're open to other ideas on how to organize and present the data to be most useful. So, so think about what would be useful for you and tell us. And then second, just tell us if if it seems like we've missed any soil parameters that would be valuable to you, because we have not yet started the fieldwork. And then any other questions you'd like to ask. So that's it for my talk. Thanks.
Hey, Katrina, can you go back? I want to add one more thing. Can you go back to the previous slide?
Mhm.
So that graph there, is that from the Stille, I suspect?
Yes, that's
Yeah,
from
so-
yeah.
Yeah, so this is this graph here is the output from a set from one of the restored sets, one of the sets in the restored site at the Stille, which underwent a levee removal restoration, I think in 2011 or 2012, when they finished the removal of the levee and dike system. And I just wanted to point out here the amazing rate of accretion that we have seen, and it goes back to the previous. It speaks to the previous presentation for a couple of reasons. 20 centimeters of accretion in 5 or 6 years. That gives us some optimism, I think, with regards to, although we're Scott and Haida were showing very high methane emissions in these restored sites, but conversely we're seeing high rates of accretion, which is on the sequestration side. So that's good. The other thing too is, at least in the Stille, and then it speaks to maybe to part of the reason why there is so much flooding in these restored sites, is that there was so much subsidence behind the levee, which was former ag site, that the elevation was actually lower immediately inside of the levee than outside in the marsh. So essentially you have to fill up this bowl before you start seeing, regardless of what the tidal channel situation is going to be, you kind of have to fill up the bowl a little bit before you're going to see great drainage. And that's all.
I have
Great.
a question.
Go ahead.
Thank you both very much. Great presentation. When we think about trying to use carbon sequestration values for carbon projects, inventories, there's always a challenge of new sites, because they're spatially heterogeneous. Vegetation's over here, but not over there. So your siting, your location of sampling is very important. And then also, one of the things we see, if we imagine a site which is, say, it's colonizing from a bare mud flat in the simplest example, the vegetation comes in and you get carbon enrichment in the root zone. So it's not just at the surface, but it's in the top 20 centimeters you get this enrichment taking place. And so one of the benefits of lead 210, when we think about all the work that was done in the Snohomish when we were there, we originally started off with the work that was done, I think, by Ron on EB Island, which had a 40-year time series of showing carbon accumulation rate at a certain time. So it seems to me one of the most valuable data sets is a lead 210 core from a restoring site of some age, because you can get a profile there that removes a lot of this variability. But then also, how do we capture the soil enrichment within the top 20 centimeters? Is there some use here in taking short cores? And then what do we do if the site is already vegetated? Then your salinity is changing. So you have a freshwater grassland becoming something else. There's going to be a lot of turnover of carbon, again, within the top 20 centimeters. Can we capture that? So I'll throw those points out there.
Hi, this is Scott Bridgham again. One thing that we found in Coos Bay looking at restored sites, and I don't think this is, actually I know it's not true of all of them, but in some cases, there is kind of a hard packed clay layer that was the base after restoration, again, depending on how it was restored. And if that's the case, you often can see that fluffy sediment that has been deposited, and it's pretty easy to see the depth of new sediment because there's a pretty clear demarcation.
Yeah. So
interesting. You should
go ahead, John. No, go on.
Just a quick aside, Scott, that was also a reason that Greg Hood was, who's been looking at channel development in the Stille, in that restoration site. You know, he also observed, Roger, maybe you can chime in here, but he also observed that the channel development was much lower than expected. And he thought it was because of that hard layer that was preventing channel erosion. So.
Yeah, that's exactly right. It's in a lot of the old ag sites, there's a plow pan that occurs just below the depth of the plow layer that is hard pan. And at the Stille site, that severely limited the depth of channels created, but they were very broad and shallow for a long time because they wouldn't cut down below that plow pan. And we did see there at the Stille, we weren't monitoring water levels really well, but we were relying on a water level logger in a channel within the restoration site to tell us what the hydrology was. And we learned that it had little to do with the hydrology on the marsh surface itself, because the marsh surface retained anywhere from 5 to 25 centimeters of water for at least the first few years because it did not drain fully. But the level logger, the water indicated that it was several feet lower than that. So we did not pick up that the site was not draining from our water level loggers. So that's just something to keep in mind.
Hey, Roger, this is Haida. I'm just wondering, I mean, I think the Stillaguamish or that area up there is pretty unique in the amount of cropland as opposed to grazing land in the Northwest. Have you seen that same type of hard pan in grazing land or only in cropland?
Good question. I guess the places I've seen it have been places that have had a mixed history of both crop and grazing on the same property, just sort of alternating over the years. So I don't have a good answer for you.
We have seen that in grazed sites, Haida. In fact, we started calling it a hoof pan because some sites that were not plowed had a really resistant, hard layer, which also affects subsurface water flow. So it's not just channel development, but water can't drain out through the soil profile either. So it's a factor in many ways.
I actually wrote a paper on the formation of hard pans under restoring sites about 20 years ago, and how they impacted the hydrology of tidal marsh restoration. And so I'll circulate that. But one of the benefits of that is that if you can use that as a marker, as Scott was saying, it would be interesting to take, just short cores and cover quite a wide area and be able to characterize the heterogeneity in carbon enrichment within the surface sediments. And, that would help us get a sense of what is the carbon accumulation within these young marshes. Because I've got a feeling that, the Felstar markers, because you only have a few sites, and you're only measuring the top, that we're really not going to get at it. And it's really the heterogeneity across the site that would be so helpful to try and characterize.
I'm jumping in here. It's time to move on to Chris's first talk. I think I'm going to create some space later on in the meeting to circle back to these questions. Seeing the limitations or the trade-offs of a Zoom meeting where, normally this kickoff meeting is pretty much an all-day meeting. We have plenty of time to talk. I hesitate to make people be on a Zoom call all day, so made it shorter, but there's a trade-off with discussion time. Anyway, we'll circle back to those later. Chris, are you ready to go?
Yes.
The stage is all yours.
All right. Hopefully you guys can see my screen, and if not, raise your hand. All right. So concurrently with the greenhouse gas emissions data we're collecting and the sequestration accretion rate data that we're collecting, we're also going to measure a variety of ecosystem drivers both in this project and in the Eastler project. And in the previous Tillamook project with Scott and Matt's measurements of greenhouse gas emissions, we also have ecosystem driver data. So the methods are very, very similar between all three projects. So as some background, previous studies have shown that soil and groundwater conditions can affect wetland greenhouse gas emissions, particularly fluxes of methane out of these systems. We also think that ecosystem driver variables are related to accretion rates and sequestration rates. The timescales are a little bit different. Usually we measure ecosystem drivers on shorter timescales. And of course, as Katrina mentioned, we measure accretion rates with radiometric dating on longer timescales. But hopefully we can find some broad differences in salinity or elevation or wetland type that correlate with the accretion rates that we're going to measure. So for example, we know that salinity is an important driver of methane. The figure on the right are data from Poffenbarger et al. That shows as salinity increases that methane fluxes out of tidal wetlands decrease dramatically. But you can see at lower salinity values that there's a lot of variability in the data. And as Scott has shown, there appear to be a complex mix of ecosystem drivers that are affecting methane fluxes. That Tillamook Bay data, those relationships can be analyzed further with the data we're going to collect from the phase 2 project as well as the Eastler project. We know also, just as by way of another example, that elevation is a key driver of a lot of processes that occur in tidal wetlands. So on the left are some data from our phase 1 project where we looked at soil stocks and a variety of ecosystem drivers. So here you can see that tidal elevation has a nonlinear but relatively strong relationship with carbon stocks in surface soils. Our metric here of elevation is a standardized value called Z star. So this relates the intertidal elevation to your tide range. So just to kind of orient you, a value of 0 is mid-tide level. That's kind of the lowest extent that you'll see vegetated tidal wetlands typically. And then a value of 1 is mean high or high water. So above that is kind of classic high marsh or tidal swamp. And you can see that carbon stocks are higher in our higher elevation wetlands. On the right are some data on plant productivity. These are short-term productivity rates over one growing season. This was an experiment we conducted a couple of years ago in coastal Oregon and in central Oregon in the Sletz estuary, where we measured total plant dry mass in mesocosms called marsh organs, and we set these out at different tidal elevations. We measured the degree of flooding in each mesocosm, and then we harvested above and below ground plant biomass for 2 species after a growing season. And you can see that the relationships are different, but the main take-home message is that elevation is a pretty important driver of a variety of processes. And we know that's true of things like decomposition rates as well. So the main research question for the ecosystem drivers component of the work, which fits in with the previous talks that have been given, is how do environmental factors such as soil temperature and salinity, groundwater level, photosynthetically active radiation, and wetland elevation influence fluxes of greenhouse gases, sequestration rate, and eventually net ecosystem carbon exchange. Some sub-questions that build on that are, how do soil, vegetation, and groundwater characteristics vary among the different wetland types that we're measuring? So how are they different between our least disturbed marshes and swamps, disturbed wetlands, and then restoring wetlands? And are greenhouse gas emission rates linked to vegetation type? So is there a relationship between the plant community composition and the fluxes that we are seeing? So you've seen this map a couple times before. These are the 5 estuaries where we're collecting the data. Methodologies are very similar between all of the sites. And just a couple of pictures of the wetland types that we're looking at. High marsh, typically, or in a few cases, we have lower elevation marsh, forested tidal swamps, and then pastures. And this is just a summary of the types of ecosystem driver data that we're going to collect. It's the time scale over which we're collecting it and some information on the sampling frequency. So in the previous talks, it was already mentioned that we're going to be getting emissions data over the course of a year on a 6-week sampling frequency. And then using the 3 techniques that Katrina summarized, we'll be collecting data on carbon stocks, accretion rate, and carbon sequestration rate. For the ecosystem drivers, we're going to be measuring soil temperature. So we'll have subsurface loggers that measure soil temperature every 30 minutes and give us a nice time series at the site. We're going to measure groundwater level also over the course of a year, every 30 minutes. Groundwater salinity, again, every half hour. We'll measure pH, and that will be spot sampling. So each time the teams go out and measure greenhouse gas fluxes, they'll get spot samples of pH in little groundwater wells that are right next to the chambers. We're going to measure photosynthetically active radiation. So that will generally just be done inside and outside the chambers at the times that measurements are made. But at a subset of sites, we're also going to collect yearly time series. So we can see if there are certain estuaries that have greater levels of irradiance than others based on rain and fog cover and so forth. We'll measure wetland elevation. We'll just do that once, probably in this coming summer or the following summer at our sites. And we'll also assess plant cover and biomass sort of generally at the sites, as well as within directly within the chambers where the flux measurements are made. Then some supplemental data include barometric pressure time series, so we can correct the water level data. And then at a handful of locations, we'll also measure channel water levels so that we can compute more local tidal datums. And we'll also capitalize on NOAA tide stations or NER swamp stations to give us additional channel water levels. Okay, so I'll go through these individual methods a little bit more. And this is kind of just a schematic that shows how we are laying out all the types of measurements we're doing at an individual site. So just to kind of orient you, hopefully you can kind of see my cursor here. This is just a very generic site where we have a main channel or creek that goes through the site. We have some kind of upland, it's usually forested. And our greenhouse gas chambers will be generally positioned along a transect that's perpendicular to that main source of tidal inundation. So that's what these little symbols mean here. They'll be kind of spread out about 10 to 15 meters apart to give us some elevation gradient. Typically, we have an elevation gradient where it's a little bit lower towards the channel and generally gets higher as you go towards the upland. We'll have that groundwater well that's situated near the greenhouse gas emissions transect, and that will have our groundwater time series as well as our soil temperature sensor. And then on the right, you can see the distribution of some of the other data that we're collecting. So we'll use the groundwater well as kind of a reference point, and we'll select random directions and random distances from that groundwater well to do vegetation plots where we'll assess plant cover and diversity and composition. And I think it makes sense to co-locate right next to those vegetation plots both our feldspar plots and our deep cores. And as Katrina mentioned, this will be a great opportunity for us to compare a couple of different methods. So I think we're going to try to put those feldspar plots and deep cores right next to each other. And then this third diagram, the same site with our groundwater well and then our greenhouse gas emissions transect. We'll also collect elevation data using RTK GPS methods and or leveling in places where we can't get good satellite coverage like forests. And this will allow us to kind of get an overall site elevation. And then for the Eastler project, we'll also be doing modeling at a few sites. So we want a very good digital elevation model of what our wetland looks like. Okay, a little bit on specific methods of wetland surface elevation. So at most of our sites where we have no tree canopies, we'll be able to use RTK GPS. At other sites, we'll have to use leveling from a benchmark or a RTK point outside of the forested area. The data will be in geodetic datum or NAVD88, and we'll convert those values to tide relevant metrics such as mean high water or the Z-star that I showed earlier. And the Z-star, I use this metric for, I don't know, 5 or 6 years now. I really like it. I first came across it in the Swanson et al. Paper that describes the warmer model in 2014. But it's a way to standardize inundation across a geographic gradient because we have different tide ranges as you go up and down the coast. This is just some NOAA data that I pulled out here. You can see with latitude from California, Oregon, Washington, up to Alaska, that our tide range increases pretty dramatically as you go farther up the Northeast Pacific. And you can also see that even within individual states, particularly once you get to Northern California, you can have a lot of variability in your tide range, even within one band of latitude. And this is due to differences in the geomorphology of estuaries and so forth. So this is a way to kind of standardize into a common metric and look at elevation gradients and how they affect our greenhouse gas fluxes and then the other things we're measuring. For groundwater level and salinity, this is a picture of our typical groundwater well. We developed this methodology in the Stocks project and other projects that Laura Brophy has led over the years. And inside the groundwater well, we have 2 loggers. We have a hobo water level logger that goes typically about 1 meter below ground, and that gives us a time series of water level in the groundwater. And then we also suspend an Odyssey logger. That's this little blue logger here that measures conductivity and gives us a time series there. And we suspend that inside the well so that it's about 25 centimeters below ground. And that gives us an idea of the salinity that is present in the root zone. So that logger isn't necessarily flooded all the time. We can figure out from the water level logger when it's immersed, but that gives us a sense of the salinity that the plants are experiencing and the salinity that's most likely to be relevant to the greenhouse gas fluxes that we measure. We process the logger data by doing a barometric pressure compensation. That's pretty standard for these types of measurements. And then we can derive a variety of metrics from the time series. So we can look at daily, monthly, seasonal values, means and maxes, for example. We can look at the daily groundwater range, how much the groundwater is moving up and down during the tidal cycle. And we can measure things like cumulative saturation of the root zone. And then we'll be doing measurements of plant cover and biomass. Again, kind of we'll focus this during the growing season, probably between July and August, kind of the peak period of the growing season in the Northwest. For plant cover and biomass, we will have about 10 plots per site. This will just give us an overall sense of the species composition at individual sites. We'll measure cover visually. And then we will also, at I think a subset of sites, assess above ground biomass. And we'll have to sort of figure out how to do this in the chambers because we don't want to harvest all the biomass during the course of the year. So I think we have a little bit of work to do to think about how to measure biomass and kind of maybe we'll collect percent cover data and then use some allometric equations to kind of estimate biomass in the chambers during the course of the year. And then one discussion point that our team really hasn't talked about much is whether we'll also want to try to assess below ground biomass. I've done below ground work, of course it's very time consuming, but it may be kind of an important metric that we can measure in our chambers as well and try to relate that to the gas fluxes that we observed. So if you guys have any comments about that and when I'm done with these slides, I'd love to hear your thoughts. And then just in terms of statistical methods, I don't want to go too deep into the weeds, but I always like to kind of think of the kinds of methods we might use to analyze the data before we've even collected it. I think we can use a variety of univariate and multivariate approaches to explore relationships between our ecosystem drivers and our flux measurements and our carbon sequestration rates. One method that I've been kind of interested in is called quantile regression. This is just a figure from kind of a popular ecology paper that shows quantile regression. And the idea with quantile regression is that you're actually fitting either the upper or the lower boundary of a distribution and relating that to your independent variable, which would be an ecosystem driver in this case, that you're measuring. This is an example, I think it's a fish example of, yeah, let's see, trout per meter of stream. And they're looking at its relationship with the width to depth ratio of the stream. And you can see that if you just sort of fit the median of your data, you have no relationship here. But you can see that the upper boundary of this relationship seems to be important. And you can use quantile regression to estimate that relationship. It's very helpful when you have limiting factors to use this type of approach, because we may see, for example, that salinity is a limiting factor in our methane fluxes. And I think that was actually kind of illustrated by the Poffenbarger et al. Figure I showed towards the beginning of the talk, where you can have a lot of variability load at low salinity values, but salinity may be a limiting factor on the amount of methane that's produced by the microbial community. And then not to go too far into the weeds, but Scott already kind of showed this method here, which is classification and regression trees. This is a multivariate method that allows you to basically stuff in a whole bunch of ecosystem drivers into your model and kind of assess the relative importance of different drivers. And then for plant communities, we can use multivariate techniques such as multi-dimensional scaling or canonical correspondence analysis to kind of see if there are certain assemblage types that may have higher greenhouse gas fluxes than others. So for the ecosystem drivers, we're hoping that the data will supplement a couple of products that come out of this study, as well as the Eastler study. So I've just kind of outlined a couple of those here. I think we'll probably have a manuscript on carbon sequestration rates that builds on both the Eastler and the phase 2 project. So the ecosystem driver data will help with that manuscript. I'm sure we'll have at least one paper on greenhouse gas emissions, again, from both projects. And then I think the ecosystem driver paper data that we collect can also inform another potential manuscript built on this project and others, which is once we convert formerly tidal wetlands into pastures and then restore them, what do those major land cover changes do to the soils, vegetation, and the groundwater? So we already have a lot of data on that from the phase 1 project. We measured 6 pastures in that project. We'll have some new pastures in the phase 2 and some new ones in the Eastler project. So I think this would actually make a really nice data set for the whole Northwest to generate a paper on that question. And then I'll be working on completing a paper that I've already started on ecosystem drivers and carbon stocks values that's based on the phase 1 project data. So just a few discussion points here for all of you. Do you think we've included all of the most important ecosystem drivers that are likely to have large impacts on greenhouse gas fluxes, or anything come to mind that we're missing that would be relatively easy to add to our sampling? For you as end users, which of these ecosystem drivers is likely of most interest and importance? And are there any remote sensing or other rapid survey methods that would be good for some of the drivers that we're measuring? I think that's my last slide.
Thanks, Chris. That was great. Anyone have any questions or comments based on Chris's discussion points? Not hearing a lot of discussions. Is any, I have a suggestion. Oh, Lisa Marie has raised her hand. You are officially recognized.
Yeah, I'm sorry for being so slow to figure this out. I'm so excited about the continuous data that you're collecting, and I think the clever analyses of it is what's the most fruitful. So, for example, wavelet analysis. What's the scale of variability that really matters? What's the how does variability change with elevation type, and so on? And so I think, just like you were getting into all the quantile regressions and the CART and all these things, this is, for me, the most exciting thing that you're doing that nobody else is doing, Chris. And so, yeah, I just want to encourage you to do it. And I think some of the questions that we might have will emerge later based on some of that fine-tuned analysis of the continuous data rather than just sort of averages.
Yeah, I'm really excited about this data set, because with the 3 projects, we sort of have an unprecedented, I think we will have an unprecedented amount of data. And I think that will really allow us to look at some interesting statistical relationships that would be harder if we just had smaller sample sizes.
Yeah, agreed. Thank you.
Steve, you have your hand raised. You are officially recognized.
Thank you, Chair. Yes, yeah, that last question you got there, Chris, about relationships to land cover. And I think that would be, for the work that we're looking at inventories, we're really trying to, I guess we're trying to step through 3 levels. There's the national level, there's the state level, and now we're getting down to the site level. And to what degree do land cover classification maps inform us about carbon sequestration and methane emissions? It's really good to know. And then can we nest it? And so when we look at data sets which are collected at the state level, which tend to be not time series data sets in terms of having more than one snapshot, but a single snapshot, does that give us the resolution to look at salinity, how salinity affects particularly methane emissions across the landscape? And then can we use a national level data set to give us a time series of change if we look at the same pixel? So I guess my long-winded question is, it'd be great to see if you can relate land cover classification schemes to the parameters that you're measuring and the variability in them.
Yeah, that's an interesting thought. I mean, I think we can probably go back into other data sets, and given we've got locations for our sites, of course, we can look at NWI. I know that people love to hate NWI, but we can look at NWI, for example, and see how our sites are classified in that scheme. We can do a CMEX classification for each of the sites in our study. I know less about kind of the national scale soil databases like I guess NRCS I think has one, but I'm sure there are experts on the team who could help kind of figure out what the soil classification levels are for our wetlands and whether that shows any correlation at all with the fluxes that we're measuring at our sites. I did want to comment very briefly on salinity because salinity is complicated, as you guys all know, and even when we have a year-long time series, which is very fascinating to look at, we know that salinity varies within a day. We know that it varies between neap and spring tides. We know that it varies spatially. Some sites are going to be tidal fresh all the time, like in the Columbia River. Other sites may swing wildly from tidal fresh during the spring to mesohaline or even polyhaline in kind of late summer and fall. So it'll be interesting to kind of figure out how we can relate the complex time series to the fluxes that we see.
I have I don't know how to raise my hand iconically, so I'll just do it.
Laura, you can just talk. Just start talking.
Thanks, Chris.
I do.
You know, one thing that really interests me too is Lisa's comment about the time series, the continuous data. It strikes me that's absolutely true that that high resolution temporal data will give us the key to understanding the relationships between drivers and greenhouse gas emissions. But I wonder about the scale, perhaps a bit of a temporal scale mismatch if we're only measuring greenhouse gas emissions for a short period of time at, you know, distant time spacings. So how do we cross that scale gap?
I think, yeah, that's a great question. And I've also thought about the temporal scale mismatch when it comes to ecosystem drivers and sequestration rate, because as Katrina mentioned with our cores, we're really looking at a century scale of kind of average accretion rates that we're measuring. And do we know what the salinity was like at our sites 20 or 50 or 100 years ago? So we are going to have to kind of make some assumptions, and it may make sense to kind of bin our sites more coarsely in terms of salinity. Maybe we'll bin the data and compare tidal freshwater with oligohaline, with mesohaline sites, for instance, and kind of make some assumptions that salinity hasn't changed dramatically over the last century. As to the greenhouse gas flex data, you're right, there is that temporal mismatch. We can certainly align, you know, we'll carefully record when measurements are made so we can compare exactly what the groundwater is showing with the flex data that we have. Maybe Scott has some additional thoughts on that since he's done a lot of these measurements before.
Yeah, I mean, there's two basic ways to deal with this. And it's been dealt with in many other different sorts of circumstances at different scales. You could either use a statistical technique. So we looked at the classification and regression tree. So even though we're only explaining 28% of the variance, we might do better with a bigger data set. And we can try some other sorts of techniques, for example, using the quantile regression and just looking at some of the higher fluxes, which I think is well worthwhile. The other way is to use more of a mechanistic model that, but then the results are only as good as the model relative to the data. But I mean, that's basically it, is you collect the point data with the results for the greenhouse gas measurements, and then you understand it statistically or in a more conceptual framework within a model. And once you do that, that allows you to extrapolate to other time periods and scales.
It makes sense if we're sure that our data are collected across the full range of the drivers of interest during the period that's important for understanding, which I would guess is all the time. So, you know, is that I love that we can analyze the relationships for those times we sample, but there still are only limited times that we sample. I guess that's what bothers my mind.
Well, I mean, there's other data too, that eddy flux towers collect data continuously. In Nisqually, Lisa Marie was sort of led one group that had that in the Pacific Northwest. There are numerous towers in the San Francisco Bay Area doing this, and if we get funded, we'll have some in Oregon. So, but I mean, those have the disadvantages. You're doing it at one tower, which has a footprint, which is relatively large, but it's spatially extensive. And what we're doing is actually the opposite. It's spatially extensive and temporarily limited. And you know, I think the best one can do is take those different kinds of approaches and look at them. And in fact, I briefly mentioned that there is a group putting together all of the chamber data and tower data for the continental US and examining it together. And they may come up with some thoughts on how to extrapolate those. But as with any science, there are limitations in what's practical. And so we've chosen spatially extensive sampling in this case.
I'm going to jump in here just to mention to Chris that we're moving into his time for his next session. So it's up to you how much you want to keep talking about this. So I'm flexible if you are.
Yeah, I'll just make one last quick comment. And I think, well, so let's see, between the 3 projects, I think we're going to end up with at least 40 sites, which is really kind of amazing. Maybe it's like 45. And we're going to be measuring, I think, 8 times over the course of the year. So if my math is correct, that's over 300 data points that we'll have. So for example, if we're looking at one variable, which is groundwater salinity, we'll have a statistical data set that has over 300 points looking at relationships between like methane flux and salinity, for instance. So you're right that there are kind of large temporal gaps in the flux data, but I'm kind of hoping with sort of the scale at which we're looking at things that we'll be able to see kind of some important relationships.
Actually, the next item on the agenda is a quick break, but we could just power through and save ourselves a little time for discussion at the end.
Could we take like a 2-minute break so I can get some water?
Sure.
All right.
So let's take a brief break. I don't have a 2-minute timer, but I'll be back in 2 minutes.
All right.
What yummy snacks are you eating, Craig? Oh, don't talk with your mouth full, though.
Okay, I think we're back. So thanks, Chris, for the first presentation. Now, about ecosystem drivers. Now, you're going to shift over to talk about expanding the database that you got started in phase 1 project, right?
Yes. Okay. Thumbs up, we can see that. All right, so I'm going to be talking about the Pacific Northwest Blue Carbon Database. And as Craig mentioned, we started that in the phase 1 project, I guess about 3 years ago. And the database was one of the major goals of the phase 1. We also call it the stocks project when we're just talking about the different working group projects that we've been fortunate to have had funded over the years. And the goal there was to assemble a regional database of blue carbon data. The original focus was on carbon density and carbon stocks data from Northern California up to Washington, particularly from emergent marshes, seagrass meadows, and forested tidal wetlands. The kind of the core of the database was the data that we collected as a team, as a science team in that project. I think that was 204 cores distributed geographically and across these different wetland types. By 2020, I had sort of expanded the database to include most of the Northeast Pacific coast. I work in California quite a bit, and I've long had interest in wetlands in Baja California and Alaska, although I haven't been able to do any field work in those regions before. So by, I guess, about last year, the database had grown to include data all the way from La Paz in Baja California to Ketchimak Bay in Alaska. And we also included data that came from a couple of other wetland types that we really didn't focus on in the phase 1 project. So we included tide flats, mangroves, that would be Baja only, of course, and then restored wetlands. This slide, I think I've showed this in past meetings, but these are some example uses of the blue carbon database by various end users, including yourselves. So managers, policymakers, and folks planning restoration can use information on blue carbon stocks and how they vary by wetland type or subregion within the Northeast Pacific. Carbon sequestration rates by wetland type, those type of data would be very valuable to carbon market developers, restoration planners, of course. And then a couple of other examples are listed here on the slide. So the hope is that the database will serve the needs of a wide variety of blue carbon data end users. Geographically, the West Coast of North America is really fascinating from a lot of perspectives. So we know that there's a very strong climate gradient from kind of the very wet coastal forests of Alaska and the Pacific Northwest to the Mediterranean type ecosystem, that Mediterranean type climate that goes from about San Francisco Bay down to the middle latitudes of Baja. And then the southern tip of Baja, of course, is subtropical. So we have this really strong climate gradient. We also have a really big tide range. I showed a slide that kind of illustrates that in the previous talk. The tide range gets dramatically larger as you go up towards the Gulf of Alaska. And then we have a wide range of different types of wetlands, estuary size, degree of coastal developments, and so forth. And there are kind of distinct subregions within the Northeast Pacific. These are the ones I kind of think about. We have the Gulf of Alaska and British Columbia, the Salish Sea, which can be sort of thought of as a giant estuary, a fjord type estuary. The Columbia River estuary the Columbia River is one of the largest rivers in the United States. It's kind of its own beast, as Heidi and Amy can explain further. The outer coast of Oregon and Washington, we have temperate rainforest. The outer coast of Northern and Central California, we're getting a more Mediterranean climate. San Francisco Bay Delta is actually our largest estuary on the Pacific coast, and a very interesting system. And then we have Southern California and Baja California, which are quite a bit warmer than other regions. So as for wetland types in the database, we have all 5 of the wetland types that we sampled in our phase 1 project. So seagrass, low marsh, high marsh, forested tidal swamp, and pastures. And then, as I mentioned, we kind of expanded that. So we have a little bit of data on scrub shrub wetlands, although the data are sparse. We've been adding data from restored wetlands, usually marshes, disturbed sites where we have that information. Tide flats is kind of a comparison with seagrass meadows, usually about the same tidal elevation, and then a little bit of mangrove data. And when we set out to construct the database, these were all the types of blue carbon data that we could potentially have incorporated into the database. So not to go into too much detail, but sort of read the left-hand side, we have carbon stocks and density data, above ground plant biomass, you can include below ground as well, soil accretion rates and carbon sequestration rates, greenhouse gas fluxes, and then measurements of allochthonous inputs or exports from the wetland itself. So these are sort of lateral fluxes into and out of wetlands. And that's a lot. So what we did in the phase 1 project is just focused on a subset of these measurements. So we built the database mainly around the soil carbon density and stocks data, and then also collected, when available, accretion rate and carbon sequestration rate data. So the text in black is what we have kind of built in the database so far. And then the text in blue is what we're proposing to add to the database in this phase 2 project. So mainly we'll be adding greenhouse gas flux rate measurements, mainly from field chambers. And if people have strong opinions about that we need to include eddy covariance flux data as well, please let me know. That feels like sort of another beast, but we can certainly think about that. And then we'll also be adding additional stocks and accretion rate data that we have both from the phase 2 project and Eastler project, as well as other data sets that come up. So what are the sources of the data? Well, the vast majority of the data has actually come from members of the working group who have just worked on many different projects over the last, well, actually going back several decades. I think Ron Thum's accretion rate work from his 1992 paper, that I think is our oldest data set, but so most of the data have come from the working group itself. We've also been able to acquire some data from literature searches and the Smithsonian CCRCN database, which is of course international in scale. We have a Twitter account, and via social media, I've actually sort of made a couple of connections too with other researchers that have been kindly providing data. This is just a very, this is just a brief overview of some of the studies that have been incorporated into the database so far. We have at least 33 published and unpublished data sources that we've been able to compile. I have a couple additional data sets in my inbox that are just waiting for a good chunk of time that I can add them to the database. They cover, again, a wide geographic range and a variety of wetland types. And you can see that the stocks data are the most numerous. So we tend to have a lot more stocks data than we have for accretion or sequestration rate. This is just a really simple schematic of what the database looks like. It's I hesitate to call it a database because it really sort of lives as an Excel file at this point. They're flat files that are linked by a unique study ID as well as a unique core ID. And then the data are kind of divided up into information on the core location and environmental variables. And then we have another, it's a pretty complex flat file, but it shows the bulk density, carbon content, accretion rate, and carbon accumulation rate. That's separated by vertical stratum inside the core. And the database has grown, so it's not just reported values that we've accumulated from studies, but we've actually been deriving some of our own values as well, and trying to do that in a consistent manner. Because one of the challenges of incorporating such a heterogeneous data set is that people did things in different ways. They sliced cores differently, they used different methods. Some people measured %C, some people measured % organic matter. So we have to kind of make all those data talk to derive synthetic values from them. So the reported data are generally bulk density, %C or %OM by LOI, and then accretion rate. And then some of the derived values are the average carbon density per depth interval. So for example, calculating the average carbon density in the top 50 centimeters of the core. We convert %OM into %C. And then we can calculate a stocks to a given depth because all the cores are to different depths as well. The additional non-carbon data that we're incorporating into the database are some metadata. So for example, the latitude and longitude of the core when it's known. If it's not known, we can kind of substitute in a general site latitude, longitude. Of course, we have the estuary name, the state and province where the data were collected, the wetland type. These are the codes that I'm using in the database: tide flat, seagrass, emergent marsh, scrub, shrub, forested, mangrove, and pasture. And then the disturbance status of the particular wetland. The environmental data, that's kind of a work in progress. When we have a core elevation in NABD88, we add that information on dominant vegetation type. A few studies have sediment grain size, and some have nitrogen or pH data. The salinity part is a work in progress because, as I mentioned in my last presentation, salinity is very complex and it's got this varying temporal component as well. So figuring out how to succinctly summarize salinity is kind of a challenging thing and something that's kind of ongoing for the database. And of course, a lot of studies just don't have either a time series or even a spot measurement of salinity. So there are a lot of data gaps in the environmental drivers. This is another schematic of kind of how the database is structured. So everything's linked by an ID. And because the database so far is built around cores, it's really a point measurement. I think the chambers will work in the same way. There are also point measurements that have a specific latitude, longitude, and elevation. So we'll sort of treat those like we're treating the core data. Linked to that is information on the position. So again, kind of where it's located. Where available, it's linked to a variety of environmental data. Again, a lot of data gaps there because every study was kind of unique. For the core data, we have two major types of, actually, I missed one here. We have three major types of data. We have nitrogen in some cases, we have bulk density in all cases, and then we have % carbon or % OM. That's the little thing I missed on here. And then for a subset of cores, we also have a soil accretion rate. That's generally by lead-210 or cesium-137. We have a little bit of set data, and we have a little bit of carbon-14 data, which is kind of its own time scale. But when we have both carbon density and soil accretion rate, we can derive a soil carbon accumulation rate. So that's kind of how the database exists currently. And then I just want to go through a couple of summary statistics about the current state of the database. We have about 930 cores that I've entered to some degree. About 850 of those cores have depth-specific carbon density values, and about a quarter of those have some measure of accretion rate, again, usually lead-210 or cesium. On the left is the distribution of the cores by states and geographic provinces. So the bulk of the data are from British Columbia to California. I think most of the data sets in my inbox are from California, so I think that bar will grow considerably. And then this is the distribution in terms of wetland type. So the bulk of the data are from emergent marshes and seagrasses. So those are the wetland types that have been sampled most comprehensively along the Northeast Pacific. This is just a map. This is actually an older map. There are probably more cores, but this just shows the location of the cores in Washington and British Columbia. So a variety from Puget Sound, and then some from the outer and inner coast of Vancouver Island. And then we found this cool unpublished data set up here in the Skeena estuary that we helped them publish that on the CCRCN database. So one of the values of the database is that we can identify data gaps, and a lot of those data gaps became really apparent a year or two ago when we held our workshops and tried to kind of summarize information. So we know that one large data gap are woody wetlands, so Sitka spruce swamps, willow swamps, twinberry swamps, for example. We just don't have a lot of data from those ecosystems. But from Boone's paper published last year, we know that these are hugely important in terms of the amount of carbon stocks they have. And it will be really fascinating to see what kinds of greenhouse gas flux rates we get from these wetlands as well. We need more data on accretion and sequestration rate. So we have a lot more stocks data than we have accretion rate. And again, that's particularly from woody wetlands and restored sites and pastures. The smaller estuaries are actually quite poorly sampled. So this is a map from Laura Brophy's recent paper, and this just shows all the estuaries and tidal wetlands in the Pacific Northwest, and many, many dozen sites. A lot of these are very small estuaries from which we have very little or no data. And we also need more data on the depth of the peat layer. So even in the Stocks Phase 1 project where we sampled to 3 meters, we don't necessarily even know if the peat layer goes another 2 or 3 or 10 meters down. So it's very hard in a lot of these wetlands to know exactly how much carbon is stored all the way from the surface down to bedrock or a sand layer. So the peat layer depth is really sparse. Okay, so in terms of the database and the Phase 2 project, we plan to expand the database by adding new stocks, accretion, and sequestration rate data. That will probably primarily come from the Phase 2 and Eastler cores that we collect. But I've really been surprised at how many data sets are actually out there. And so it wouldn't surprise me if we come across a couple more going forward. And then we're going to add a new module that includes our greenhouse gas flux measurements, both from this and related projects and any other flux data that are available along the West Coast. So I'm not really aware of any other teams doing these measurements in the Pacific Northwest, but there may be some, and hopefully we'll collaborate with them and be able to include their data as well. And then another major goal is to make progress towards a regional synthesis of carbon sequestration and greenhouse gas emissions for the region. So it's a lot of work to pull the database together. It's a lot of work to kind of standardize a lot of the variables that need to go into the database. But I think there's a lot of value into making a stab at providing a synthesis of all the data, because we can certainly share the database in part or in whole with others, but it would take a lot of additional steps to kind of make sense of the data that we've collected. So for greenhouse gas emissions data, our initial focus will be on point measurements that we collect in the chambers, and we will, this is kind of my thinking so far, we'll include flux values for 3 gases, so carbon dioxide, methane, and nitrous oxide. And we'll code each measurement by its date, so it's year, month, and day. Hopefully all those values are known. And then just like we've done with the soil core data, we will add supplemental data to those point measurements. So latitude, longitude, and elevation, vegetation, pH, or other values that are known. And then one thing that we haven't collected for the stocks core data that will be important to add for the greenhouse gas measurements are air and soil temperature data sets, because we know that temperature can have a role in flux values. And then one of the derived values that we may be able to calculate from the reported fluxes of these three gases are annual estimates of fluxes. So if we have a time series over the course of a year, as we will in this project, we can calculate an annual flux and include that rate as well. So this is what the database will hopefully look like when we add the greenhouse gas data component as well. So that's this little module down here. And with the combination of greenhouse gas flux data and estimates of soil carbon accumulation rate, we can get an estimate of kind of the net carbon exchange over time from the wetlands. And then in terms of products from the database, of course, the database itself is a substantial product alone, but we hope to also be able to produce a synthesis publication that looks at across this whole region, so it incorporates our data as well as other studies published and unpublished to synthesize what we know about soil accretion rates and carbon sequestration rates for all these different wetland types for the west coast of North America. And of course, we'll have at least one manuscript that will summarize all of the greenhouse gas emissions data from the work that Haida, Scott, and others are leading. In terms of data availability, this is kind of a complicated question because the database as it currently stands is a mix of both published and unpublished data. So I'm happy to share any of the published data, which is probably most of it at this point. But people have been very generous sharing data sets with us, sometimes in an unpublished form. So if you have a data set that's unpublished, please check with me, and I'll try to check with the original authors first, just to make sure that they're okay sharing those data. A lot of the data sets that we've been able to, that have been published are either already available on the CCRCN's Carbon Atlas, or we've worked with James Holmquist and his technicians to get those Northwest data sets into the database. So a lot of what's in the Pacific Northwest database you can already find on the CCRCN. We do have some unpublished data as well. And then towards the conclusion of our project, we'll also be sharing the data that we specifically collect with the NERS CDMO interface, which you can use to usually access a lot of their hydrology data. Okay, just a quick check of the time. So a couple of discussion points. Since the database is fluid and we're sort of working with the data that are available, are there other types of supplemental or supportive data that are interesting to you as blue carbon end users that you would like to see summarized in the database? What formats and platforms would you like to see the data? Is there a desire to see all of the point data kind of in its more raw form? Is there interest in seeing more summary statistics for particular regions or wetland types, for example? So what level of summary and aggregation are most important? I can share the whole database with you now, but it's 15,000 lines of data. So I imagine that a lot of end users are going to want some level of summary to kind of minimize the amount of the work that they have to put into to using the database. So that's all I have, and just open it up to comments and questions.
Thanks, Chris. Anyone? Comments?
Chris, this is Ron. Thank you very much for your work on this. And those that haven't submitted their database, you can expect an email or a call from Chris daily. But but thank God he helped me, pushed me to find the data set I had from the early 90s. But anyway, this is great. You know, I don't really know as far as the data summaries I might want, but you know, I can see where it's going to be of great value to have this database together. So you can query it for information you need. So thank you, Chris.
Yeah, I'm so glad you were able to hunt down your original notebook. That was a fun story.
Chris, I'm thinking that one of the outputs that we do towards the end of the project is maybe do a training over Zoom about how to access data in different formats, either through the CCRCN Coastal Carbon Atlas or other formats. So let's keep that in the back of our minds.
Yeah, that's a great thought. And one comment that I'll make about the CCRCN database, there's a lot of overlap, but there, I guess, two key differences. One is that we have some unpublished data that they don't have yet. Well, hopefully they will have it eventually. But the second is, as I've pulled data sets off the CCRCN, it's great. They have this wonderful spatial carbon atlas, but they just present the data in its raw form. So they don't calculate some of the derived characteristics that we're calculating. So for example, carbon stocks to a half meter, carbon stocks to a meter, average carbon density, interpolation. So if they're missing a particular depth interval, they just leave it blank. We're actually interpolating between the depth interval above and below that. So those are some differences. And one of the reasons we went down that road is that in order to publish a synthesis as a paper, we needed to, actually derive some of these values. So I just want to point that out.
Great. Other comments, questions? Steve, you have your hand raised.
I do. Yeah, thanks for that, Chris. That was great. One of the things that we're going through on the CCRCN, and maybe relevant here, is the question about how do you present data to people who need the data. And on the one hand, there are the Chris Janiseks and the James Holmquist of the world who can extract the data and then work out, let's say emissions factors from it. And I think for when we work with the data, we'll probably work with that sort of process where, we'll write our own R code and we'll extract the data as we need it. But for many inventory compilers, and this might be relevant for each of the states you're working in, they might rather have a way that the data is packaged for them. So if they can get some way of getting an annualized emissions factor for different wetland classes, which has the confidence intervals described as well, then they would like to maybe just extract it like that from a data set. So when we think about different users, there's the high-end user and there's the people who just need the data. Mm-hmm. So we can talk further as you're moving forward about that kind of information that might be needed.
Yeah, for sure. And I'd love to collect thoughts from end users earlier rather than later, because that may also influence how we structure the database as we're kind of putting in data. When we have a sense of what end users may want, that will influence the formatting, and we can kind of get that right from the beginning. So at any point, please send me your thoughts, send them to Craig, myself, anyone on the team, as you're thinking about the way in which data summaries will be most useful to you. Please send those along.
Yeah, definitely. Actually, we're thinking about it this month, and so we'll get you back some ideas really fast.
Great, thanks.
I actually had another question, Chris. In your disturbance status, you've got, if I recall correctly, natural, disturbed, and then restored. And the disturbed has several subcategories that might be of interest, especially given the conversation we had earlier. And I wonder how possible it is to include like ag type, pasture versus cropland, or even actively managed versus abandoned. those sorts of statuses. And again, I know a bunch of these are, data that are coming into you, and those subcategories may not be there, but maybe it's good to include those bins.
Yeah, that's a great thought. I'm trying to remember for restoration, obviously we have both active and passive restoration. That's kind of a rough way to divide those up. I may have encoded for that already. I can't remember, but if not, that's certainly a very valuable thing to add. And then for disturbance, that's a great thought. I think we should try to figure out a way to code by, at least for the non-tidal sites, the pastures, we should try to think of a couple of classes for the different types of agriculture that occurred on the site. Another type of disturbed wetland, well, two other types of disturbed wetland we could have is, one is muted tidal, right? So we have kind of a non-natural tidal regime. I can't recall if we actually have any cores from that type of disturbance, but that would be interesting. And then I know we have some seagrass cores from British Columbia that I know there are sort of disturbed meadows, and I can't remember the nature of the disturbance. So as much as we can code is great. You do raise a point, which is sometimes we get a data set and we may have a latitude, longitude, but we don't have the information on the disturbance level. So there may be some GIS work that will hopefully partner with members of the science team who do more GIS than I do, so we may have to just go in and figure out some of this stuff. I recently started adding a data set from, let's see, it was the EPA's National Wetlands Assessment, and they did both freshwater and tidal wetlands throughout the continental United States. I think over 600 cores in that database. I partitioned out the tidal wetland ones for the West Coast, which was, I don't know, maybe 20 or 30 cores. And they had information, they had kind of their own land classes. And then when I used their lat long and just sort of simply put it into Google Maps, they were calling, there were some areas that fell behind dikes, so they were probably non-tidal sites, but they were calling them estuarine. So the point being that there's some work to kind of work with, we can't just throw in the data as is. We have to kind of QA a lot of it so that it's consistent.
Yep, I hear you. Okay, we're impinging on my last session, which is not a problem. What I wanted to do with this last session very quickly is just to get some feedback from everybody about how we should proceed with everybody providing feedback and getting information about how we're doing on this project, and then open things up to a discussion to, as I said earlier, circle back to some of the conversations or issues that we wanted to spend a little bit more time on. So when it comes to official end user feedback, as you recall from the timeline that I put up, we have 2 more of these that we'll be doing, sort of checking in on the status of the project. And then there's one at the end. Where we wrap up and share with everybody how things went and what the outputs are going to be. And in between, judging from the previous projects that we've done in a similar way, there's always conversations that come up between those official meetings. So please don't feel like you have to wait until these official meetings to ask questions, make comments, or even check in about what's going on with the project. I can be a conduit for that. You can contact me in between these official meetings, and I can do what I can and then, get you to other people who know more than I do, which is most everybody, as needed. And then, or you can contact people directly who are doing the work in the field. So if you guys have suggestions about how you'd like us to share information with you and keep the conversation going, now's the time to bring up some comments. Not hearing many comments or questions. Okay, then.
Well, Craig, just to
Yes,
mention, as we're working, looking at the natural working lands project, you're on that team too, and so we'll continue to have discussions, and maybe you're the best conduit to help feed things back to this project. Though I'm happy to reach out to people individually, let's just,
Okay.
as the discussions are going, let's just keep tabs on who we should be talking to.
Yeah, I think that's the plan. And then,
Craig,
yes.
oh, sorry. I just wanted to say that I guess I'm a little bit out of the loop compared to some of you, like Steve, about all of the other things that are going on at Restore America's Estuaries and Pew Charitable Trust and so forth. So I wonder if there's a way to get some reverse information flow.
Good point. Yes, let me think about that. It could be as simple as just shooting an email out to everybody. That where we headed slide, where we mentioned a couple of examples of kind of next step natural climate solutions type projects. I can send everybody a summary of where that's headed. And I just saw Sylvia from Pew mentioning that she's willing to, I think, join that effort in some way, shape, or form. So good point, Haida. Other comments? All right. All right. So again, circling back, what are some of the issues that you guys want to sort of talk about a little bit further? We had Scott and Haida's gas emissions talk and all those issues, Katrina and John's sequestration talk, and then Chris's two ecosystem driver and database talks. Thanks, by the way, for those excellent presentations. Who wants to kick off getting back to what we were talking about? Somebody be bold.
I'm not bold, but I'll be naive, or I'll jump in.
Oh, Jude, you're bold.
I'm trying to wrap my head around the question that I had earlier and what prompted my. I'm looking through my notes, but I think okay. So, Scott's the data that he presented. So we often go up in front of to defend the research we're doing, and one could interpret the emissions on newly restored marshes as justifiably so, saying, well, it looks like restoring marshes is really not a good way to offer short-term mitigation for greenhouse gas emissions, and 100 micromole per meter squared per hour over 10 years that it takes a marsh to stabilize is just in thinking through that and talking through that would be helpful, because we kind of just cross our fingers and hope that they will reach that point. But the other question I had about those, and Laura and Scott were talking through this, are those excessive, those high rates with the newly restored marsh, are those sort of an artifact of the fact that the way we restore marshes now with too much inundation and not enough drainage just makes them a high rate of greenhouse gas or methane emissions for short term that we could mitigate? Or is it just a property of restoring marshes that we are always going to have that high methane emissions just because that's the nature of these big transitions and disturbances we have from going from an ag to a restored marsh? So I guess there's two questions there. One is just the talking points for thinking about these really high rates in an early restored marsh. And then is that something that can be mitigated if we inform and adjust restoration practices, or is it just that that's the way it is when you restore these wetlands?
If it's okay, I'll attempt to address that. At Tillamook, and again, it's one site, and so we'll have a lot more data from a lot more sites at the end of this. So we'll see how transferable those results are. And again, it was after just about a year of restoration, so it's very soon thereafter. It is important caveats. We did put together an estimate of the greenhouse forcing balance or for those sites, which I didn't present because it would have been very time consuming. It's a very nuanced kind of story. And I'll present just a few of the nuances. One is the previous condition of some of those was freshwater wetland, not ag. And so they probably were even higher emitting sites previously to the restoration. And we didn't sample them beforehand. Other things is we had good greenhouse gas measurements with 8 of them over the period of time. You saw there was huge site heterogeneity. So where you pick in that restored site, you get a very different answer. And then the other thing when you do that net ecosystem carbon balance is you have to do the soil carbon sequestration rates. And we had a few lead-210 cores and then more feldspar markers. And referring back to Katrina's talk and sort of the limitations of that, but we had pretty good feldspar marker data. And so you're trying to take, it probably, when you put all of this together, is one of the better data sets for looking at this in the world, but it still had its limitations because it's a big restoration site and it's trying to put together multiple kinds of data. All of that is sort of speaking around is that hopefully when we're done with this project, we'll have good soil carbon sequestration data with both kinds of methods associated in close space with the greenhouse gas measurements. I'm fairly confident, and we've actually even looked at them in Coos Bay, that if you get a very saline site, there will be a net positive cooling effect from the restoration because you don't get methane in highly saline sites. And it's more in those freshwater ones where I think you end up with these potential trade-offs. You could restore them and add sediment to them and try to make them immediately into a high marsh. You're probably going to get lower soil carbon sequestration, but also lower greenhouse gas emissions. Laura, you probably would have some thoughts on that also.
I think you said it. We were early. There's huge variability. This is we don't have enough data yet to make any big conclusions that restoration isn't a good way to mitigate for climate change. I think we're just starting to scratch the surface of this complicated issue. So thank you, Scott, for pointing that out.
Although I feel compelled to jump in here and say what I'm hearing is everyone saying that it's a temporary situation, like early, and it's just a question of how long a restoration site becomes an emitter or is an emitter before that transitions away from that. I don't think anyone would say
That might or might.
Go ahead.
That might or might not be true, though, Craig, depending on salinity. I mean, we don't yet have data from sites later in their trajectory or from less disturbed tidal swamp sites that are pretty fresh. So I think we need a lot more data, but I do agree with you that the site is going to probably get better in terms of methane emission as it accretes sediment and as the channel system develops.
Good point about salinity. I was making the assumption that this was a site that we would normally have the salinity regime that we would expect to not have a lot of methane coming out of it.
Just to note that, you know, in a typical restoration project, well, in many restoration projects, what you would do is you'd excavate a pilot channel to the deepest depressions, because you, particularly when people are around, you try and avoid standing water on a site from mosquitoes and other reasons. And so while the channel excavation itself would, you know, be a greenhouse gas cost, we should still look at it, you know. So, you know, if that's done, then you would reduce the methane emissions on the rest restoring site from the beginning, at least on the environmental side of it. So you have to think about the different restoration approaches. Sorry, Laura.
I don't know. I was interrupting you. Sorry. I agree. There is no single low spot on a site like the Tillamook. It's 400 acres of flat ground with a microtopography all over the place. So it's really hard to excavate a channel system that will drain it properly. But that Bandon project provided sort of a way that one can move towards that with adaptive management. So this isn't something we can't do anything about.
I'd like to just add, and I think Scott alluded to this earlier, but a couple of the sites in the SFC project in Tillamook that had really high methane fluxes also they were ponded. So we know that because we had groundwater time series there, and we also frequently visited to download those loggers, but they were kind of unusual. So they were ponded, they stayed wet basically all the time, either at the surface or above the surface. So that, I think, is just an artifact of kind of where we sampled. And then if you looked at some of the other, and the values were so high that they drove up the mean considerably for the entire site. And so if you looked at the non-ponded areas at SFC, I think typically the wetland or the methane emissions were lower.
Yep.
Yeah.
I've got to go. I've run by. Sorry.
Thanks, Laura.
Thank you.
I was just going to say that officially the meeting is wrapping up in 1 minute, but if you guys want to stick around for a few minutes for some final discussion, that's certainly doable. I'll just take this time to thank everybody a lot for taking 3 hours of your day to help us think through this, and to the presenters today. Thank you very, very much. So I will stay in touch with notes, etc., and keep everybody in the loop for the duration of the project. So thanks again for sticking around. Speaking of sticking around, are a bunch of you or a few of you interested in continuing the conversation? Yes, no, maybe. Chris, or
a couple minutes.
Yeah, okay, a couple minutes.
I have to run. I'm really sorry. Great to see everybody and hear everybody. Thank
okay,
you.
Thanks, Haida. All right, Jude, have we satisfied your question about methane emissions restoration sites?
Well, I mean, I didn't need to be satisfied, and I want to make sure that it's clear that this was not a referendum on this amazing, important pilot work that Scott and others are doing. Like, it's, you know, so I'm just out of the gates. I'm saying, like, this is great work we're doing. I'm just mulling through these things. Also, of course, if we just think myopically about carbon emissions, and that's the only way to evaluate restoration, then that's something to think about, but that's not, these restoration projects do so many other things besides worry about carbon capture, like habitat, blah, 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 everything you all know very well more than I. So,
benefits.
yeah, so thanks, Scott, for talking through some of that, the nuances.
Yeah, well, I was going to add in next, one of the things you said is that I think in the end, when we get all of this for these multiple projects, we will find that some areas pencil out in terms of carbon and greenhouse gases and some don't. And I think that'll be the answer.
Right.
We'll have a much better sense of which ones do and which ones don't. And I would agree, just what you said before is we know that for estuaries, they have many other ecosystem benefits that are probably much more important than the carbon. It's just the current driving paradigm for much of this. And that doesn't mean that it isn't worthwhile to restore these other sites, even if they do have a small net warming effect.
And Scott, is it accurate to say that we'll be able to refine the salinity and especially salinity and temperature thresholds for the Northwest on especially methane emissions?
I'm sure we will. I'm not positive it will be a lot cleaner story, but we will have sampled over a very broad set of sites, broader than any other study that I'm aware of any place in the world, maybe for any category of wetland. And so I think we will know the true variation across those gradients and make the best estimates that any team could do based on a data set available.
One other thing, oh, sorry.
I'm done.
Go, Amy.
I just was going to say, I think another important piece that'll come out of it is looking at a wider variety of restored sites and also different ages. Not only different salinities, but just different kinds of topography and hydrology and drainage and age, all those things, which I hopefully will help clarify the story.
I also want to add, John, here that, going back to Jude's question about when you're trying to justify a particular project based upon ecosystem good and service, and I think everyone here already knows this, but if you look at a case by case, site by site basis, we find that these restoration sites are the restoration efforts are relatively small in acreage. So, we're not getting huge global impacts from any one restoration. And so I would similarly suggest we're not going to, either the positive or the negative. And if, to justify and the kind of money that we might make from a carbon market is, on the order of maybe perhaps funding the monitoring efforts, not funding the restoration itself. So I think that on a case-by-case basis, you absolutely have to look at the multiple benefits that would accrue from a restoration and not just tie it only to the blue carbon piece.
Yeah. I think that's kind of where we got to with the feasibility assessment. But, in terms of greenhouse gases, saline wetlands sequester carbon, what's it, net GHG removers, forested tidal wetlands because of the biomass. And the emergent marshes and low salinities and the soils from the forested tidal wetlands seem to be about a wash in that methane emissions and carbon sequestration, give or take, balanced out. Though we really didn't, there's a lot of variability in there. And as Scott's data was showing on the restoring site, it really depends upon where you're sampling as to how that pencils out. So I think that's kind of what we're holding for the greenhouse gas emissions estimate is that kind of assumption I just mentioned. But there might be opportunities through better understanding the data for reducing methane emissions associated with restoration practices. But as you say, John, still that might be small because the sites are small. But when we think about what could happen in the future with seal rise, like big settings like the Skagit, which is, very important agricultural land right now, but, it might not be held as agricultural land indefinitely into the future with sea level rise. There might be large scale restoration activities take place in some places like that. And so it's helpful to think through what those longer term implications are. If we can, for instance, restore forested tidal wetlands back in the system again.
Yeah, absolutely. And along those lines with sea level rise, the blue carbon is just intimately tied to accretion. And, the alternative of not restoring it is not sustainable in the face of sea level rise. I mean, especially these ag lands directly adjacent to the dikes. I mean, at some point you can't drain them anymore, or at least not and make a profit with your agriculture. So that, in terms of you're encouraging the sequestration. Part of that is blue carbon, but a part of that is resilience to sea level rise as well. It's really, in the long term, the only option.
Hey everybody. I just wanted to add on to that, and what Steve had said is some work that we've been engaged in on the East Coast and Cape Cod. This discussion about what that the current condition is not necessarily the baseline. And so when we compare restoration, over a longer period of time, it's not comparing it to what we see today and maybe this sort of dry pasture or semi-wet pasture. It's what we expect to see over time with sea level rise, which could be a much wetter system, which could have methane sort of emissions associated with it. So I realize that sort of time scale is the question, but I do think it's a good consideration, when we think over a longer period of time, to keep that in mind.
Yeah, good point. Thanks, Scott.
Good.
Hey, everyone, it was good to see you. I've got to take off. Thanks for this good work.
I think it's probably time to wrap it up unless anyone's got quick final comments. Okay. Thanks, you guys. Thank you very, very much for the input. We'll be in touch. Take care.
Thanks, Greg.
Greg, thanks everyone. Greg.
Thanks, everybody.
Thanks, everyone.